Alright, so this video we're going to take a look at the limit of a function. Alright, so this video is looking at limits and using tables to calculate limits, which using a table to calculate limits is not really a good way at all to find the limit of a function. The next video we will look at, or the next video I'll have be right after this one, is calculating limits using limit laws, and that's how you're going to find limits. Okay, but this video is to get you to have an understanding of limits. All right, so the intuitive definition of a limit: suppose f of x is defined when x is near the number a, then we write, all right, so I know my handwriting's a little messy here. This is LIM. This is the limit of f of x as x approaches a is equal to some number L. And we say the limit of f of x as x approaches a equals L. If we can take the values of f of x arbitrarily close to L by restricting x to be sufficiently close to a on either side of a, but not equal to a. So that's important there. You've got to understand, whenever you're finding limits, we're not saying that x is equal to a. We're saying that x is getting close to a. Okay, that's what the limit is. It says, okay, as x is approaching this number, it's getting real close to this number, x is, then what's y getting close to? That's what we're finding with limits. And here you can see we have some figures here. This right here, if x is approaching a, then the limit is approaching some number L. All right, and then here's two other ones, and you can see in this first graph here, the function is actually defined at a. Okay, it's defined at a. But in these next two examples, the function here, it's defined at a, but it's here. This is the y value at a. So in other words, whatever function this is, if we plug a in for x, we would get this as a y value. But the limit of this function as x approaches a is this y value up here, this L. Okay, and then this one right here, this function is not defined at a. You can see there's a hole in the graph there. But the limit as x approaches a would be L, because just like it said here, okay, it's getting closer and closer to L as a gets closer, as x gets closer and closer to a on either side. So you can see as we come in from this left-hand side on a, and as we come in from the right-hand side over here, we can see that it's approaching this hole here, which it's approaching this y value right here. Okay. All right. So hopefully this will make sense, all of this. Students tend to struggle with limits quite a bit when they're evaluating them. So let's look at this. Guess the value of the limit of x minus 1 over x squared minus 1 as x approaches 1. Now what we're going to do is we're going to make a table of values. So basically what we're doing here is we're approaching 1, and you can see the values here, we're coming from this side. We're getting closer and closer to 1 from the left-hand side. See how we start out here at 0.5, and then we get to 0.9, and then we get to 0.99, and so on. And same thing over here. We evaluate at 1.5, 1.1, 1.001, and so on. We're getting closer and closer to 1 from the right-hand side. All right. So what we're doing with the table is we're taking these x values, we're plugging them into the function to see what we get. So if we plug 0.5 0.5 in for x here. Okay, so I've got 0.5 minus 1 over 0.5 squared minus 1. That gives us 0.666667. That's what we would get if we plug the 0.5 in for x. All right. And then we would plug in the 0.9, the 0.99, so on. So we would plug each x value in for x. And I'm going to go ahead and fill these values in, and I'm going to pause the video when I do it, and when the video resumes, it'll all be filled in. All right, so I've got the table filled out. So I just took each x value, plugged it in for x, and got the y values, okay? And, you know, if you're bored, you can pause the video and do all of these yourself, but, you know, there they are. So they want us to guess the limit. So for this problem, you can see that x is getting closer and closer to 1 from this left-hand side over here. We're coming in from the left. And you can see what the y values are doing. It looks like that this function, the y values are approaching 0.5. And the same thing here, as we're coming in from the right-hand side, these values 1.5, 1.1, and so on, you can see the y values, it looks like they're getting closer and closer to 0.5 also. So if we were to guess the value of this limit here, we would say it's equal to 0.5. Okay, and like I mentioned at the first of the video, this is not a way to evaluate limits. Okay, we'll evaluate a limit like this in the next video when we learn the limit laws. That, I mean, we can do this in a couple of steps. Okay, it's not difficult at all to do, but like I said, you've got to understand this. You've got to understand what the limit's doing. Okay. All right, so now let's take a look at this. We've got g of x is equal to x minus 1 over x squared minus 1 if x is not equal to 1, and it equals 2 if x is equal to 1. All right, so this is a different function than the one that we just worked. I mean, it looks close, but this is the function in the first example, but this one, this is a piecewise function. Now, if we look at this, okay, let's just take a look at the graph of it. Okay, let's see what this graph would look like. All right, and you know, for this function, you may have to get a calculator or some computer software to graph this thing to know what it looks like. But if we're here at 1, and then we've got a y value of 0.5 here, there's going to be a hole right here, and this graph is going to do something like this. Okay, it's going to do something like this. And then, so that's for this first part of the graph when x is not equal to 1. But when x is equal to 1, we have a y value of 2 up here, and so we would have a 2 right here. Now, if we took the limit of this, okay, if we took the limit of this, some of you may think, well, okay, the limit as x approaches 1 of g of x, some of you, you know, just looking at this say, well, it's 2, you know, because that's the y value. But understand that when we're finding limits, it's not the y value at 1. It's not the y value when x equals 1. It's the y value as x approaches 1. As x approaches 1, what is y approaching? So you can see from this graph, as we're getting closer and closer to 1 from the left and from the right, you can see these y values, they're getting closer and closer to this 0.5. And so this limit would have the same value as the first example, okay? Even though it's a little bit different, okay? All right, so hopefully this helps you understand that when we're finding the limits, it's the limit as x approaches the number, not when x equals the number, because when x equals 1, that's 2. In other words, we could write g of 1, okay? And we're not taking the limit here, but we could write g of 1 is equal to 2, okay? Because that's the y value when x is 1. See, when x is 1, our y value is 2. All right, so let's look at this one. So let's estimate the value of this thing. So we've got the square root of t squared plus 9 minus 3 over t squared. All right, so, and we're finding the limit as t goes to 0. So what we're doing is we've got 0 here. We're coming in from the right. We're coming in from the left, okay? So, you know, we could start out with 1, and we could start out with -1 over here, and we could get closer and closer, you know, say 0.1, and we could do negative 0.1, and we could do 0.001, and we could also do negative 0.001. All right. Now, to save yourself some time, you notice over here on the t values I have plus or minus, okay? There's no sense in plugging in 1.1, 0.001, and -1, -0.1, -0.001, and so on. There's no sense in plugging in the positive and the negative of that number. Because if you look at this problem, and this can save you time if your teacher has you do a table on the test, this can save you some time. Look what I'm doing with the t value. I'm squaring them. Well, 1 squared is 1. -1 squared is 1. See? When I plug +1 and -1 in for t, they're going to have the same value. I'm going to get the same value when I evaluate this because I'm squaring them. Okay? So I hope that made sense. So if I plug in +1 or -1, I'm going to get a y value of 0.162277. All right. And then I'll plug in the plus or minus 0.5. All right. So this is what I got when you plug them all in. Okay. Now, from this limit here, we can see that this limit, it looks like, as I'm coming into 0 from the right and the left, we can see that it looks like this thing is approaching 1/6. Okay. Now, is that the answer? Okay. That's what we're looking for. Well, if you do this, let's see, square root of t squared plus 9 minus 3 over t squared. I'm going to show you, you'll kind of see in this one why it's not really a good idea to use tables. And I've got a couple more examples where you'll see that too. But I could carry this out even further. I could do plus or minus 0.001, plus or minus 0.0001. So you see what I'm doing? I'm getting even closer and closer to 0. Okay? Getting closer and closer to 0. And when I do that, okay, so just remember, based on this table, here we get 1/6. So here I get 0.1. I get this. Here I get 0.16667. And here I get 0.167. And then here I get 0 when I plug this into when you plug it into a calculator. That's what you get. So you can see this value here is the closest one to 0, right? I mean, this number's closer to 0 than any of the other ones. All right, and if I added, this has 5 zeros in front of the 1. Well, if I had 6 zeros in front of the 1, what do you think I might get? I might get 0 also, right? All right, so what's happening here is when you plug this into your calculator, so when you get really, really, really close to 0, okay, so this, once again, this t value is getting really, really close to 0. So what's happening is when you're plugging this number in for t here, you've got point squared plus 9. You're taking the square root of that, okay? And when you plug this into your calculator, okay, let me do that real quick. Okay, so when I plug that into my calculator, I put in 0.000001 squared plus 9, and my calculator returns 9 as an answer. And then we know the square root of 9, okay? This right here is the part underneath the square root, and then you take the square root of that, you get 3 minus 3 is 0. So your calculator is returning 0. Okay, so this is giving you a false value because your calculator is only going to be able to take it out to so many digits. Okay, so that's why tables really aren't good to evaluate limits. And like I said, the next section is how we're going to do limits. But you know, all the time I see students on a test, they'll get to a problem on limits, and the first thing they'll do is make out a table. Okay, don't do that, okay, unless your teacher in the problem specifically says calculate this limit using a table. Okay, but you know, if we did take this table further and we added these values to the table, you would come up with the limit is 0. Okay, but that's not correct. The limit of this is actually 1/6. Okay, all right. So I know all of this can seem confusing, but you know, just kind of stick with it. This is just to help you understand about limits. All right. All right, so what about this one? Let's guess the value of the limit of sine x over x as x approaches 0. All right, so once again, we're going to come into 0 from the left and the right, just like we did in the previous problem. And so I'm going to be plugging in positive values when I come in from the right. See, if we're here at 0, as I'm coming in from the right, I'm going to be plugging in positive values. If I'm coming in from the left, I'll be plugging in negative values. Now you can see here, I've got the plus or minus on the numbers, because if I evaluate this at positive 1, I'll get the same answer as if I evaluate it at negative 1. And let me just show you how that works. So this will be kind of a good little review on trig for you. So if I do the sine of 1 over 1, okay, that's plugging 1 in. Now, let's plug in the sine of negative 1 over negative 1. Well, remember your negative angle identities in trig, that sine of negative 1 is the same thing as negative sine of 1 over negative 1, and the negative and negative make a positive. Okay, and so you can see I'm going to get the same result whether I plug in the positive or the negative of that number. Okay, and what you'll do is you'll have to plug these into your calculator. Okay, you'll plug these into your calculator and evaluate them. Now, the important thing here is you've got to make sure when you're evaluating these trig functions you've got to make sure your calculator is in radians, okay? If you put your calculator in degrees, you're going to get the wrong answer. You've got to be in radians. And so I'm going to go ahead and do all these. I'll just write the first one down. That's 8414709.8. And then I'll pause to do the other one. So I just plugged in 1, punched it in my calculator, and got this number. All right, so I've finished filling out the table, and you can see what the values are doing. You see what these y values are doing. They are getting closer and closer to what number? What is this number approaching? Well, it's approaching 1. Okay, and that would be your answer. And you'll see if you watch these videos. There's one in chapter 3 that I'll be doing, and this would be chapter 2 in a calculus book, probably the second section. It's the second section in the Stewart calculus book. But in chapter 3, we'll actually prove that this is 1 if you want to watch that. Okay. All right, so let's look at this one. We've got the sine, the limit of sine of pi over x as x goes to 0. All right. So what I've done is I've gone ahead and I've picked some values. Okay. I didn't come in from the left and the right. I'm just going to come in from the right just to show you something. So if we plug 1 in for x, if we plug in 1/3, 0.1, 1/2, 1/4, and 0.01, whenever you plug these x values in, guess what you're going to get for an answer? You're going to get 0 for every one of them. Okay? You get 0 for every one of them. So that might lead us to believe that you're going to get the limit is 0. That's what we would think. And look, if you plugged in the negative of those, you would get 0 also. Okay, you would get 0 also. And so we might write, well, the limit is 0. Well, this is wrong. Okay, it's wrong. So what I've done is I've got a graph of this thing, and it might be kind of hard to see, but this is what the graph looks like. Okay, this is what the graph looks like. So you can see we come in here like this, and then look what happens as x is getting close to 0 from the left and x is getting close to 0 from the right. It's hard to see, and I even think if I zoom in real tight on this, I don't think you could even see it then. Well, you can see how the lines are kind of splitting apart a little bit. But basically what this thing's doing is you're getting closer and closer to 0 from both sides. It's just bouncing back and forth from -1 to 1. Okay? You see this thing's going from it's going up to 1, down to -1, 1, -1, 1, -1, so on. All right. It just so happens that the values, the x values that were chosen here, those values gave us 0 as an answer. Okay, that was these values right in here. But if we would have moved over just a little bit more, you know, in between those x values, then we would have been up here somewhere, or we would have been down here, or we would have been up at 1 or -1. Okay, so that's another another point, that tables are not a good idea to evaluate limits. Okay, you've got to be really, really careful. And so since this thing, as we're getting closer and closer to 0 from both sides, and it's just bouncing back and forth from 1 to -1, then this limit here does not exist. All right. And you know, watching this video, you might be thinking to yourself,
you might be thinking to yourself, well, I still don't know how to calculate limits. Okay, well, yeah, no, you don't, because we haven't learned it yet. Okay, you haven't done it yet. Okay, that's going to be the next video, but this video is important to watch. And also, in a minute, I'm going to be doing some limits that equal infinity or negative infinity. You might want to watch those. Okay, you definitely want to watch that. And we'll talk about vertical asymptotes. That's important too. All right. So let's see what we've got here. Okay, so this one, find the limit of this function here. Okay, so as we did before, we're going to plug in these x values here. So when I plug in the 1, I'm going to get 1.3428, and then let me pause and fill it. All right, so here's another one that, you know, about using tables. So when we plug these x values in, and yes, I know I'm just coming in from the right hand side right now. Okay, I'm coming in from the right hand side, but let's just look at this. So we've got these y values here, and based on this, if we look at this, we say, well, that limit's going to 0, right? It's going to 0. Well, if you carry this on out, let's say we do 0.05, then we're going to get 0.000100009. And then if we plug in 0.01 for x, we're going to get 0.0001. Okay, so, you know, that kind of makes us look at this a little bit differently. Okay, a little differently. Maybe it's not going to 0. Okay, but, you know, like I said, if we stopped right here, we would think, well, it's going to 0. But see how we're getting smaller and smaller. But look, these numbers, these last 3 numbers here, pretty much the same thing, just about. Okay, so this limit here is actually 0.0001, or we could say 1 over 10,000. Okay, same thing if we write it as a fraction. And that's that's the disadvantage of tables. Okay, and you might be thinking, well, if I do a table, how do I know how many numbers to do? How do I know how close to get? And that's the point I'm trying to get across to you, is don't do tables. Okay, this is just to help you understand limits. That's what this section is. Okay, and actually you'll see later on, and you'll see how this will make more sense why it's 1 over 10,000, because later on you'll see the limit as x goes to 0 of cosine of 5x. Cosine of 5x, you'll see that is equal to 1. Okay, and see, there's your 1 over 10,000, and then we'll also see that the limit as x goes to 0 of x cubed, you'll see that's 0, and so you'll actually have 0 plus 1 over 10,000, which is just 1 over 10,000. Okay, some of you watching the video, you may know how to get that already, but for those of you that don't, that's in the next video, the next section. Okay, so you might be thinking, well, why don't we just get to how to evaluate limits? Okay, yeah, we're going to do that, but that's what's so important about calculus, is not just, okay, I know how to calculate this, I know how to calculate this. You need to understand this stuff It's going to make it a whole lot easier throughout your calculus career. Okay, all those calculus classes you've got to take, it's going to make it so much easier. But you've got to understand this stuff. All right, so let's look at this example. We've got the Heaviside function, and it's defined by h of t is equal to 0 if t is less than 0, and it equals 1 if t is greater than or equal to 0. All right, so, and we want to find the limit of this thing as t goes to 0. Okay, as t goes to 0, what's the limit of h of t? All right, so we've looked at tables. Okay, so let's look at a different approach to finding these limits. So some functions that we come across, you know, like this one, it might be difficult to evaluate the limit, but we can easily find the limit from the graph. So sketch the graph of this thing. So if we graph this thing, let's do that. So there's 1, there's 0. All right. So if I graph this, we can see that h is equal to 0 when t is less than 0 and 1 when it's greater than or equal to 0. So this is the same thing as graphing y equals a number, right? Y equals a number. So what does the graph of y equals a number, what does that look like? Well, that's a horizontal line, right? Going through what y equals. So if you look at this bottom one here, and I draw that, y equals 1, that graph looks like this, doesn't it? You see that? That's the graph of y equals 1. But remember, it's only y equals 1, and remember, h of t equals or y equals, that means the same thing. So if we have y equals 1, that's only for values of 0 to infinity. So that means that we would not have this part of the graph. It would only be from 0 to infinity. Okay? So this graph, y equals 1, or h of t equals 1, would just look like that. All right? And is 0 included? Yes, because it's greater than or equal to. So this would be a solid circle. Okay. All right, now let's look at this one. Y equals 0. Well, that's a horizontal line where y is 0, or just the x-axis, right? So from 0 back to negative infinity, our graph would be this. All right. Now, is the 0 included? No, the 0 is not included, so we would have an open circle there. And so hopefully you can see already that the graph, I'm sorry, not the graph, but this limit, hopefully you can see it does not exist. Okay? And the way that we know that is because, remember, I mentioned earlier, we're coming in from the left, we're coming in from the right. Okay? So now we're starting to talk about one-sided limits. Okay? One-sided limits. So if I take the limit as t goes to 0, okay? Now let's come in from the left. So as t goes to 0 from the left, that's what this little minus sign means. I'm taking the limit of h of t as t approaches 0 from the left-hand side. I want to know what that equals. And then I'm going to also take the limit of h of t as t approaches 0 from the right-hand side. So I'm going to come in from the right-hand side. So let's look at these. So if I take the limit as t approaches 0 from the left, so I'm coming in from the left-hand side, and as t is getting closer and closer to 0, well, what's my y value? It's approaching 0 also, right? So we would say this is 0. And then as I'm coming in to t from the right-hand side, well, I'm coming in from the right-hand side. What is my y value approaching? It's approaching 1. See, I'm getting closer and closer to a y value of 1. So we would say that is 1. Now, do you see how the limit from the left and the limit from the right, they don't equal each other? So that means this does not exist. And so that would be your limit. Okay? All right. So that leads us to this, the definition of one-sided limits. So we write the limit of f of x as x approaches a from the left is equal to some number L. That's the notation, which I just went over it. And similar, this right here is the limit of f of x as x approaches a from the right. Okay, so all this means is that x is getting closer and closer to a from the left-hand side. This one means x is getting closer and closer to a from the right-hand side. Okay, so that's your one-sided limits. And so now, well, let's see. Before we, no, we'll go ahead and go to this. So we've got the limit of f of x as x approaches a is equal to L, if and only if the limit of f of x as x approaches a from the left and the limit of f of x as x approaches a from the right, if both of those are equal to L. So that's pretty neat. So if the limit from the left and the limit from the right are the same, then that's the limit as x approaches that number a. Okay, so they have to be equal. Okay, the limit from the left and the right, in order for this limit to exist. And you saw that in this example that I worked right here. You could see they weren't the same. They weren't approaching the same number. Okay. All right, so for this one, it says, use the graph of function g, and I did not write that, but this whole graph here is function g, to state the values, if they exist, of the following. All right, so we want the limit of g of x as x approaches 2 from the left-hand side. Okay, so here I'm coming into 2 from the left-hand side. I'm approaching 2. Well, what part of the graph am I on? I'm on this one up here, right? So I'm coming in to 2 from the left-hand side, coming into 2, and my y value is approaching what? It's approaching 3. See, the y values keep increasing as I come into 2 from the left, and so I'm getting a y value of 3. So this limit would be 3. Now, the limit of g of x as x approaches 2 from the right-hand side. All right, so now I'm coming in from the right-hand side. So if I'm coming in from the right-hand side, I'm up here on this graph, and you can see as I'm getting closer and closer to an x value of 2, my y value is getting closer and closer to 1. And so this would be 1. So this is the limit as x approaches 2 from the left. This is the limit as x approaches 2 from the right. So now for part C, they're asking us, well, what's the limit as x approaches 2? Well, we just saw that right here, didn't we, with this? So we just calculated the limit from the left and the right, and we got different answers, didn't we? They're not the same. So this limit here does not exist. Okay, they're approaching 2 different y values. Now what about this one? The limit as x approaches 5 from the left. So as I'm coming into 5 from the left-hand side, well, you can see I'm coming into 5, so I'm here. X is getting closer and closer to 5. Then I jump down to this graph, and I'm coming in here. And so what is my y value? I'm getting closer and closer to a y value of 2. And so this is
2. And then what if I'm coming into 5 from the right-hand side? So I'm coming into 5 from the right-hand side, here. So once again, the y value is getting closer and closer to 2. Okay. Now remember that this limit, as I'm coming in from the left and the right, the limit is not 1. Okay. The y value is 1 when x equals 5. But we're doing limits. And we're approaching. X is not going to ever equal 5. It's just getting close to 5. So as we get closer and closer to 5, y is getting closer and closer to 2 from the left and the right. And so now if we want the limit of g of x as x approaches 5, well, you can see the limit from the left, the limit from the right are the same. And so that would be the limit as x approaches 5 would be 2. Okay. All right. Now, also in this problem, let's just throw something extra in there. If they ask you to do that, if they ask you to find g of 5, what would that be? That's right. That would be 1. Because, see, at 5, y is equal to 1. Okay. All right, so how about this one? The limit of 1 over x squared. Find the limit of 1 over x squared if it exists. Okay? All right, so we could go through and we could plug these numbers in. Okay, and once again, I'm coming in from the left and the right. Okay, coming in from the left and the right. And if I plug in the positive or the negative, it doesn't matter. I'm going to get the same answer because I'm squaring it. So if I plug this in, I get 1. And look, you know what? Well, let's go ahead and plug it in. So we get 4, 25, 100, 400, 10,000, and we get 1 million. Okay. So what's happening here? Okay, so I'm getting closer and closer. Okay, I'm getting closer and closer to 0 from both sides. And what are these y values doing? They're just getting bigger and bigger and bigger and bigger. So if I did 0.0001, that number would even be bigger. And the closer I get, hopefully you can picture that the function is not approaching a number. As x is getting closer and closer to 0, f of x is not approaching any number. It's just getting bigger and bigger and bigger and bigger. Okay, so it's not approaching anything. And so this limit, okay, so this limit here, as x goes to 0 of 1 over x squared, that does not exist. Okay? But in this case, we don't want to write that. Okay? We don't want to write that. This function is increasing without bound. It's getting bigger and bigger and bigger and bigger. It doesn't exist, but it's the behavior of this function as x gets closer and closer to 0. Do you see that the function is going to infinity? See, these y values, they're just getting larger and larger and larger and larger. Okay? And if we looked at the graph of this thing, okay, if you graph this thing, this graph looks like this. Okay, you can see as we're getting closer and closer to 0 from the right, what are these y values doing? They just keep increasing. They're getting larger and larger. And same thing as we come in from the left-hand side, we're getting larger and larger. Those y values are going to infinity. And that's what we want to know. Okay? We want to know that.
it's important that we know it's going to infinity or if it's going to negative infinity. So if a graph is doing that, okay, if you're doing these limits and you see that the limit is going to infinity or the limit is going to negative infinity, don't write does not exist. Tell me, is it going to infinity? Is it going to negative infinity? All right, that's going to help you a lot later on when you get into graphing these things. Okay, all right, so it's going to help you draw the graph better if you can see what that function's doing. Because if I tell you, okay, so with this, if I tell you the limit of 1 over x squared is equal to infinity as x approaches 0, well, I know as I'm going to 0, I know this graph is going to go up like this. And if I'm coming in from the left, I know it's going to go up like this. But if you just tell me does not exist, I have no idea what the graph looks like. Okay, so you're gonna graph functions in calculus, and you're going to get a lot of detail about it. So just keep that in mind. We want to know, is it going to infinity or negative infinity? So we've got a definition. Let f be a function defined on both sides of a, except at a itself. Then the limit of f of x as x goes to a is equal to infinity means that the values of f of x can be made arbitrarily large by taking x sufficiently close to a but not equal to a. All right. So, and then also a definition, let f be a function defined on both sides of a except possibly at a itself. Then the limit of f of x as x goes to a is equal to negative infinity. So, the function could go to infinity, it could go to negative infinity. And so if you looked at this, you could actually, we could come in here and draw all these things. So if I'm right here at a, and let's say I've got me a asymptote there or something. So see, I could look like that. So if I'm coming in from the left, it's going to infinity. Or I could be here, and I could come in from the left-hand side. From the right-hand side, it's going to infinity. And then here's one, if you're coming in from the left-hand side, and that would be a graph as x is approaching a from the left, the function's going to negative infinity. And then same thing here, we could have something like this going to negative infinity as I'm coming in from the right. Okay, so that's what the graphs would look like for those two definitions. And then similar definitions can be given for the one-sided infinite limits. Okay, that's actually this right here. See, I'm coming in from the left, coming in from the right. Okay, so the limit of f of x as x approaches a from the left or from the right can equal infinity, or it could equal negative infinity as I'm coming in from the left and the right. All right. So here we've got vertical asymptotes. Okay, so the vertical line x equal a is called a vertical asymptote of the curve y equals f of x if at least one of the following statements is true. All right, so for this one, you've got to show one of these. So if we think there's a vertical asymptote somewhere, then we have to say, okay, so we say, okay, there's a vertical asymptote at x equal a. Then you've got to show that one of these is satisfied. Only one of them, okay? Not all of them, you just got to do one of them, all right? So let's talk just a little bit about this, because this is really important, these vertical asymptotes and finding these things. So probably, if you've had algebra or something, you probably looked, had a function like this and said, what's the vertical asymptote? X equal 2. Okay, and that's correct. And your high school teacher, if you learn this in high school, might have said, okay, you got a vertical asymptote where the fraction's undefined. Okay, Now, they may not have said that, but that might have been what you heard, okay? Because if we have something like this, let's see, say x squared plus x minus 6 over x minus 2. So let's say we have this, and you look at that, and you might say, well, there's a vertical asymptote at x equal 2. And that's not true, okay? This one has a vertical asymptote at 2, but this one doesn't. Because if we took the limit of this as, say, x approaches 2 from the right-hand side, we would not get positive or negative infinity. If we took the limit of this one as x approaches 2 from the left or right, we would get positive or negative, we'd get positive infinity, okay? But this one we wouldn't. So the part that you probably didn't hear is that if you have a rational function that's in simplest form, okay, so this one, if we factor it, we've got x plus 3, x minus 2 over x minus 2. See how those x minus 2's cancel out? Okay, so what's happening there? And you know, you can look on your, if you got a graphing calculator or some software or something, you can graph this. What happens, what this is doing, there's a hole in the graph. Okay, so it's important that when you're asked to find the vertical asymptotes, you have to show this work right here. Okay, you've got to show that. And if you're in my class, I'm pretty strict on that. Okay, if I gave you something like this and you just said x equal 2 is the vertical asymptote and you didn't show me one of these limits, I wouldn't give you any credit on the test. I know I'm mean like that. Okay, so let's come up here, and before we start looking for vertical asymptotes and stuff, let's just see how to find the limit. Okay, let's see how we find the limit. So let's do this first one. The limit as x goes to 3 from the right of 2x over x minus 3. Okay. Now, I know this whole section so far, we've talked about doing the tables and everything. Okay. Forget about the tables. Okay. Forget about the tables. Let's just look at this. Let's reason it out. So hopefully you can see that if I'm actually plugging numbers in for x, I would be plugging in like 3.1, 3.01, 3.001, and so on, right? That's getting closer and closer to 3 from the right-hand side. So the one thing that I want to get you to agree with me on here is that if I'm plugging these numbers in for x, does it make sense that the numerator is pretty much 6? Okay, it's not going to be much off from 6. Okay, it's not going to make a lot of difference. But if I plug in 3.1, that denominator is going to be 0.1. If I plug in the next one, that's going to be 0.01. And if I plug in the next one, it's going to be 0.001, and so on. Okay? So do you see what's happening here? This 6 divided by 0.1 is going to give me what? That's going to give me 60. This is going to give me what? 600. This is going to give me 6,000, and so on. And you can see as I go to 3.0001, then my next one would be what? Probably 60,000, and so on. So as I'm getting closer and closer to 3 from the right-hand side, you can see that these y values here, they're just getting really, really big, right? So this limit here, we would say this is going to infinity. All right. Now, let me say this. We're fixing to find the limit as x approaches 3 from the left-hand side. Okay. But if we were asked to find the vertical asymptotes of this function here, we would be done. We wouldn't have to do anything else. This right here proves there's a vertical asymptote at x equal 3. Because what does this say? it says the vertical line x equal a is called a vertical asymptote of the curve if at least one of the following statements is true. So we only have to show that one of them is true. Okay? And we showed, let's see, what did we do? We went from the right and we got infinity. So we went from the right and got infinity. We showed this one was true. You see that? And that's it. We're done. There's a vertical asymptote there. But when you're doing this, you want to do the limit from both sides. And the reason that you want to do that is when you get to graphing these things and you start graphing these, well, you need to be able to graph it, show what the graph looks like when you're coming in from the right and from the left. Okay? Are they both going to infinity? Or are they both going to negative infinity? Or if we come in from the right, is that going to infinity? And then when we come in from the left, is that going to negative infinity? How do we draw the graph right there? And that's why you just go ahead and calculate the limit from both sides. Okay? Now, this one, we're coming into 3 from the left-hand side. So it's the same argument, or the same logic. So we're going to be plugging in numbers like 2.9, 2.99, 2.999, and so on. So hopefully you can see once again, when we're plugging this into the numerator, we're going to pretty much get 6, right? Pretty much get 6 in the numerator. But when I plug this 2.9 into the denominator, I get negative 0.1. For this, I would get negative 0.01, and this one, negative 0.001. So you see what it's doing? It's doing exactly what it did as we came in from the right-hand side, but the only difference is we're getting those big numbers, but with a negative sign in front of it. So we would say this one is going to negative infinity. Okay? All right. And that stuff that I'm erasing when I wrote all that down, you should be at the point where you wouldn't have to write that down. You could look at it and you can do that in your head. You can see that the numerator is staying at a particular number. It's not moving far from it, but that denominator is getting really, really, really small. Okay? And so you can see this one's going to infinity, this one's going to negative infinity. And if we drew this graph, we know there's a vertical asymptote here. So this graph, what would it look like? Well, it would, something like this. Okay, see, as we come in from the right, it's going to infinity. We got that from here. As we're coming into the left, from the left, it's going to negative infinity. All right. All right, so what about this one? Find the vertical asymptotes of f of x. All right, so to find the vertical asymptotes, well, we know what the graph of tangent looks like, right? So if we graphed tangent, we've got what? Negative pi over 2. We've got pi over 2. You learned this in trig. We've got vertical asymptotes here, right? And so we know there's the vertical asymptotes right there. Okay. But let's look at it into more detail. Okay. That's calculus. Okay. We're going to go in more depth into this stuff. And we want you to look at this in a different way. Okay. We want you to think deeper about all this stuff. All right. So basically what we're doing here is we need to calculate the limit as x approaches pi over 2, okay, of tangent x. And we're going to also find the limit as x approaches pi over 2, well, from the left and from the right, okay. So we're going to calculate both of those. All right, so well, what's the limit? Well, yeah, we know what the graph looks like. We know as we're coming into pi over 2 from the left, that would go to infinity. From the right would go to negative infinity. But let's look at it a little different. Okay, so if we look at the graph, so we've got 0, we've got 2 pi, 3 pi over 2, and pi over 2. All right, and there's 1, there's negative 1 and 1. So one thing we know is that tangent x is equal to sine x over cosine x. All right. Now, let's look at the graph of sine. So if we graph sine, that's going to look like this. Okay. And then if we graph cosine, well, cosine is going to look something like this. Okay, so there's sine and cosine. All right, so if I'm taking the limit, and let's approach pi over 2. Let's approach pi over 2 from the left-hand side. Okay, so you can see as I get closer and closer to pi over 2 from the left, do you see that sine is pretty much has a y value of 1? Okay, you see that y value of 1 there? But look at cosine. What's a cosine doing? Well, as I'm getting closer and closer, these y values, man, they're getting really small, aren't they? See, I'm getting y values of like 0.1, 0.01. See, as I'm getting closer and closer, see, these y values are getting really, really small. They're going to 0 also, aren't they? But this sine x, it's getting pretty much to be 1. So you can see that this 1 here over these numbers that are getting really, really small, what is that? Well, we just worked some problems like that. That's infinity. Okay? Now, what about tangent x as x approaches pi over 2 from the right-hand side? Well, guess what? That's going to be the same thing. I mean, it's not going to be infinity, but it's similar. So as I'm coming in from the right-hand side, sine is pretty much once again what? 1, right? And that's over, well, what's cosine doing? Well, the y value of cosine is getting closer and closer to 0, but they're what? They're negative. You see that? So these y values are getting really, really close to 0, but they're negative. So we can see this would be negative infinity. And you can see you've got your vertical asymptotes there. Okay? Now, let's keep going. Okay? Because it says find the vertical asymptotes of f of x equals tangent x. Well, we know tangent x has a lot of vertical asymptotes. So the same thing, and I'm not going to work all this out, but you see what we did here when we calculated the limits. Well, do you see the same thing can be done at 3 pi over 2? And then the same thing can be done where? Probably at pi over 2. I'm sorry, at 5 pi over 2 and 7 pi over 2, right? I'm sorry. Yeah, at pi over 2, 3 pi over 2, and so on. There's a pattern there. All right. So what would the vertical asymptotes be? What would the vertical asymptotes of tangent x be? Well, it looks like it's at what? 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2, negative 3 pi over 2. So Well, to get from pi over 2 to 3 pi over 2, what am I doing? I'm adding pi, right? And then if I wanted to get to 5 pi over 2, I would add what? 2 pi, because 2 pi plus pi over 2 would give me 5 pi, and so on. So it looks like my vertical asymptotes would be x equals pi over 2, and then I'm adding what? I can add 1 pi, 2 pi, 3 pi. See, I'm adding 1 pi to this, then I'm going to add 2 pi, and then if I went even further, I would add 3 pi. I would add and subtract. See, if I subtracted pi, that would give me negative pi over 2. All right, and if I subtracted 2 pi from pi over 2, that would give me negative 3 pi over 2. So I'm going to add n times pi, where n is an integer. And that would be my vertical asymptotes. Okay? Okay, so this is the last one. Find the limit of natural log x as x approaches 0 from the right. All right, so, you know, this is an example of where you can just do a quick graph. And you don't even really need to label anything. You just need to know the general shape of a log function. What's the shape of that graph look like? Well, we know that graph looks like this, right? All right, and it goes through, you know, if we plug the 1 in, that gives us a y value of 0. Okay, and that's what the log function looks like. So you can see as we're getting closer and closer to 0 from the right hand side, this graph is going to negative infinity. All right, so I don't know how many of you still here. I mean, I might not have anybody see this part of the video. I know it's a long video, but hopefully you stuck around. If you did, you learned some stuff. You're smarter now. But this section here is kind of to help you understand, okay, what's going on when we're doing limits. Kind of gives you a picture of what's going on too with the graphs and everything. But the next lesson, that's when we're going to get in and we're going to learn how to evaluate these limits using some limit laws and stuff like that. So be sure to watch that video. But hopefully this helped. Limits can be confusing. They can get kind of messy on some of them, get kind of tricky, confusing, not sure what to do. But, you know, this right here gives you an understanding of limits. This and the section before. I'd go back and watch that. And these are all in a playlist. So, you know, watch that next video, watch the one before it. But the next one, I'm gonna try to make it simple for you where you can, you know, kind of, okay, this is how you do limits. This is what you got to look for. Okay. So thanks for watching. Give me a like, share, and subscribe, and I'll see you later.